Assalamu alaikum. Welcome to Turkish Engineering. In this example, we have two reactions. First one, when we have 500 degrees of Celsius, and second one, we have 650 degrees of Celsius. And that will lead to a change in rate of reaction, okay? You have two terms in a reaction. Let's take this to this side. Will be more comfortable, okay? So we have two terms in any reaction rate. One is a function of temperature, and second term is function of concentration, okay? This is 1 and this is 2, okay? K2FCA. And we will take just the ratio of them, okay? I put K1, K2 because they are these K coefficients are dependent on temperature and activation energy, and we have different temperatures for these two reactions. So we will say that this K will be changed, and we cannot say just a constant K. And we will take actually the ratio of them. So we want to investigate how much faster we have. So just take the ratio of the reaction rates, and that is like K1, I'm sorry, this is K2. It's on the numerator, we have K2, and denominator, we have K1FCA. Anything related to concentration, that term will they will neglect each other. We have temperature change between two reaction rates, okay? So we can say that this K2, if we remember from the reaction rate term, depending on the activation energy and temperature, it's just exponential function, right? So this is T1, T2. But activation energy is property of this reaction, so it will not change. But temperatures are changing. So that means actually if you have something like same term, but powers are one is on the numerator, other is in denominator, that means you just subtract them. So you will have something like this. These are the common coefficients, and you will have 1 over T2 minus, you have this one, right? Because you are subtracting the other term. So you will have something like this. This ratio will lead to just this equation, okay? Just let's explore that value. EA, we already know the activation energy is 300 kilojoule per mole. And we have R, ideal gas constant. It will be 8.314 joule per mole Kelvin. But we want to have kilojoule per mole. So let's say we multiply this by 10 to the power minus 3. So we convert it to kilojoule per mole Kelvin. Okay. So that kilojoule and that kilojoule and that mole, they cancel each other, and you will have here Kelvin term. Okay. This Kelvin is 1 over Kelvin, and but 1 over Kelvin. So that Kelvin will go up, and here you have Kelvin terms, 1 over Kelvin terms, they will cancel each other. Let's see. Here you have second temperature, you will convert to Kelvin, okay? Minus 1 over 773 Kelvin if you add 273 to 500. So those terms, actually, Kelvin terms, will also cancel each other. So you have only a rate, okay? With no units. You will have just compare relatively how much faster. So we have unitless thing, right? Just a number. So let's see how we calculate that. So E to the power, you have negative 300 over 8.314 times 10 to the, actually we can use also this one and say minus 3, 10 to the power minus 3. Then we have times 1 over 650 plus 273 3 minus 1 over 773. Okay, so that's a huge number actually. That's a huge number, but that can happen if we have 150 degrees of Celsius, and actually it depends on also on the activation energy that will also affect the effect of the temperature. It's bigger or less. So we found the ratio between two reaction rates. Thank you for watching.